So this is the tutorial here. So before starting on the weight learning, there's one small thing that I can tell you that I probably missed about. So we were talking about all the approximate lifting procedures and how they kind of use approximate symmetries and so on. So one way of actually having guarantees on the solutions is to use it within samplers as proposal distributions. And there's been a couple of different works on that, where what they've done is they've taken the approximate distribution and used it as a proposal distribution in a sampling algorithm. For example, in importance sampling or Metropolis Hastings. And so in that way, you can kind of get guarantees as well as have the efficiency associated with the compressing and so on. But there's still a little bit of difficulties here, which is particularly some steps in these algorithms are not very scalable. For example, computing the importance weight or the transition probability in MH, they still have to do some computation that's expensive when we think about MLNs in general. So that's something that I wanted to add. So now let's look at what is weight learning. So here, given this MLN formulas and some relational data, which is this training data, you want to learn the parameters or weights for each formula, right? So again, as I said, in MLNs, the learning process is a little different as compared to traditional machine learning methods, simply because there's only one instance to learn from. So there's a single training instance. This is the full database to learn from. And then similar to inference, grounding, the MLN creates a very large Markov network, which makes the learning problem hard as well. So there are some domain-specific heuristics that people use. And when we talk about the applications, I think he'll also mention some of the domain-specific heuristics. So for example, when you do entity resolution, there might be some atoms that from domain knowledge, which will likely be true or false. So you can use that kind of knowledge to reduce the size of the MLN and so on. But in general, what we want is some domain independent tools that can make MLNs work for practical applications, so that you can use it off the shelf without actually doing some, without tweaking the algorithm in a domain specific way. So there are two main types of learning. One is called generative learning and one's called discriminative learning. So in generative learning, you basically do not assume that there are any query variables. Right, so you basically maximize the log likelihood of the model. Right? So let's say you're given these formulas in this complete relational database. So if you can think about it, a relational database in an MLN is a full world. Right? So a world is an assignment to every single atom in that MLN. Right? So that is the whole thing that you're given, and you've got to learn from it. So you're given this one relational database, which is this one world, and you want to estimate the parameters of this MLN. Right, so what the weights of that MLN will look like. So it turns out that when you do sort of maximize the log likelihood and you solve this a little bit, you're basically going to get, this is the main sort of equation that you're going to get to compute the gradient in each step, which is what you want to compute is, given the current weight assignment, what is the expected number of groundings of a particular formula that are true, right? That's the expected value of Ni. Under the current weight assignment theta, and Ni of omega is basically, given that training world that we have, how many groundings are true. So Ni of omega is basically how many groundings are true in this training data, and expected value of Ni is basically how many groundings are true under the current weight assignment that we have. Right? So what is the expected number of groundings that are true. So clearly, computing that is complicated because you need to compute the probabilities, right? So you need to get because to compute that expectation, you want to kind of compute what is the probability of, this grounding being true and so on and so forth, right? So those are all hard problems to solve anyway we saw in inference. So this is a hard problem in general. So again, so expected number of groundings is the ith formula that's true in the data using the weights theta, and then the Ni of omega is simply the number of groundings that's true in the training database. So one approach to do this in a lifted way was done, I think, very recently. It's a 2016 paper, which is this lifted generative weight learning. It's 2015, I think. So in lifted generative weight learning, what you do is you use this lifted inference oracle. So basically, we had this lifted inference procedures, right? So use this lifted inference procedure to actually compute that gradient in an efficient manner. And the way they do it is basically you can decompose this expectation as, this probability of a grounding F1 being true plus the probability of grounding F2 being true, and so on and so forth. So what you need is you want to compute the marginal probabilities for each grounding of the formula, right? So let's say I have this first order formula. I'll break this first order formula into ground formula, and I need to compute the marginal probability of each of these ground formulas being true under the current weight assignment theta, right? So that's how I can estimate that expected value of ni of omega under that assignment theta, right? So now that we want to compute these marginal probabilities, one way to do it is we can use the same sort of argument and say that I'll group together equiprobable sets of groundings together. So if I know that f of E1, so if I know that there are some 10 ground formulas that all have the same marginal probabilities of being true under the current weight assignment, I'll group them together. I'll compute the marginal probability of one of them and multiply it with how many elements there are in that group, right? So for example, I'll compute it as probability of f of E1 and multiply it by the size of this set E1, right? Probability of f of E2 and multiplied by the size of the set E2, and so on. And to compute each of those probabilities, I'll use like this lifted inference procedure, right? So specifically in this paper, they use this lifted inference procedure called weighted first order model counting, which is quite similar to the probabilistic theorem proving. So this is exact inference. So they use exact inference here and compute this expectation efficiently. So one of the main things to note here is that when you do generative learning, you're doing kind of maximizing the log likelihood. So you do not have evidence coming in. So you do not compute this marginal probabilities of these ground formulas conditioned on any evidence, right? So we said that when you have evidence conditioning, the symmetries are broken, and so lifted inference becomes harder. So when you want to do generative weight learning, lifted inference is not so hard, simply because there is no conditioning over evidence, right? So the symmetries are intact, and so you can do this kind of computation in a more efficient manner. But of course, the structure of the MLN should allow for lifted inference. And when you want to compute those sets of equiprobable groundings, the problem might be that there might be too many of these sets, right? So there might be too many of these sets, which simply means that the number of computations that you have to do might be extremely large, right? So those are two problems that are associated with this generative learning process. So again, so the problems with that is that what if the MLN structure does not allow lifted inference? So again, if I give you an arbitrary problem and an arbitrary knowledge base like this might just not allow any sort of lifted inference to be applied at all, right? So you cannot really kind of compute this expectation easily using lifted inference. So that's a problem. And the second thing is that the same approach will not work when you want to do discriminative weight learning. So in discriminative weight learning, what we do is that we assign a subgroup of variables as evidence, right? And there's another group of variables which are the query variables. And what we want to do is maximize the conditional log likelihood instead of the log likelihood, which is you take the log, you basically compute the likelihood given that these variables will always be given as evidence. Right, so in practical applications, discriminative learning works slightly better than generative weight learning, simply because you know some additional information or knowledge that these kinds of variables will always be evidence to your inference problem, right? But now that you want to condition on some of these variables, you cannot really use the same procedure here, because as I said, when you condition on certain evidence variables, those symmetries are broken, and now lifted inference becomes much more harder to compute, right? So the same procedure that you use for generative weight learning cannot be used for discriminative weight learning, because you have that evidence problem coming in. So we need some other kind of technique to actually do this. So this was a technique that we proposed a couple of years ago to actually use what are called approximate counting oracles to compute this gradient in a very efficient manner. And this is applicable to many different kinds of discriminative learning procedures. All right, so the idea again is that you want to compute that gradient in an efficient manner, which is n of ni of omega minus expected value of ni of omega under the assignment theta. So now we can see that computing this ni of omega, in fact, it turns out to be a sharply hard problem. So what I mean is, if I give you a complete assignment or a complete world and a first order formula, and I'm asking you how many groundings of this first order formula are true in this complete assignment, right? So it's almost like answering, you can think of it as answering a conjunctive query, which says that I'm giving you this database and I'm asking your query saying how many, count the number of times that some conditions are satisfied, right, for this particular database. And that is a sharply hard problem in terms of the number of variables in that particular clause. And of course, computing expected value of ni of omega is, as we saw, is even harder because you now need to compute those counts over all possible. You need to compute the expected value of the counts, which means you need the probabilities in general, right? So now the idea here is that to solve this counting problem, we'll encode each formula as a graphical model. So now you had this formula, right? So we want to encode the counting problem as this graphical model sort of counting problem. And the key property is that if I can compute the partition function of the graphical model, then I can do counting in that, then I can compute the counts ni of omega in an efficient way, right? And I'll show a brief example to make this a little clear as to how exactly we do that. So again, so the idea is that every formula will encode as a graphical model, and we'll say that if I can compute the partition function of this graphical model, then I'll be able to actually compute the number of groundings that are true for that particular formula in a relational database. And to compute the partition function, we'll use these approximate counting solvers, and there are many of them, and they work pretty well, to get these counts in an efficient manner and use that to estimate the gradient. So let's take this simple example, which is you have this formula in which you have not r of xy or s of yz, and the domain of x, y, and z are all the same. Let's say it's a and b. Right? So let's say we are given a particular world which is like this: r of a is 1, r of ab is 0, r of ba is 0, r of bb is 1. And similarly, you're given the assignments to s as well, which is something like this: s of a is 0, 1, 0, and 1. So now the task is, given this kind of assignments, I want to compute how many groundings of not r of xy or s of yz are true. So that would be the counts that I want when I'm computing the gradient, the ni of omega that I want. And one way to do this is, basically I'll convert each of these into potentials of a graphical model, right? So what I'm saying is that I'll take this RAA, RAB, RBA, and RBB and convert it into a potential which has two variables, x and y. And the potential is saying that, if RAA is equal to 1, for x is equal to a, y is equal to a, it is equal to 1, the value of that potential out there. So the way to do this, to decide on whether to use an identity function or an inverse function, is if the sign is negative, then you use an identity function to map from this world into the potential. And if the sign is positive, then you use an inverse function to map from this sort of original sort of world into that potential there. But essentially what you're trying to do here is that you're trying to kind of get the solutions of this graphical model to be equal, or get the partition function of this graphical model to be the same as the number of groundings that are satisfied in the formula using this evidence over here, right? So if you do this mapping this way, what you will get is basically that, and that's what is shown in the paper. And the advantage of this is that you can sometimes compute counts in a very efficient manner as compared to using a naive counting approach. So I'll give you an example here. So let's say I have this chain sort of formula, which is R1 of X1, X2, R2 of X2, X3, and so on. So it's a chain of, I have n different variables here. So if I have n different variables here, basically there are d to the power of n possible groundings here, right? If d is the number of groundings that each of these variables can take, or d is the number of objects that can be substituted for each of these variables, I have d to the power of n possible ground formulas here, right? And if I want to compute how many of these ground formulas are true, in a naive approach, I need to go over each of these things, right? And say, is this true in the current database? Is this false in the current database? Right? It's a very brute force sort of naive approach to do that. But let's say I convert this into the graphical model, which is looking like this now, because x1 and x2, there's a potential between them. x2 and x3, there's a potential between them, and so on. So it turns out that the encoded graphical model has tree width equal to 2 here, right? So using this graphical model, if you see what's the tree width of this graphical model, it's equal to 2. So now, using efficient inference algorithms for graphical models, I can compute the partition function of the graphical model in time or space, which is O of d cube. Because the tree width is equal to 2, so I can compute it in O of, exponential in the tree width plus 1 time and space, right? So instead of going over d to the n possible groundings, I can actually do this in O of d cube time and space. So in certain cases, when the encoded graphical model has low tree width, then I'll be able to compute the counts in a much more efficient manner. So that's the intuitive idea here, as compared to doing this sort of manual or this naive counting approach. And this is inspired from something that they also do in databases when you do conjunctive queries. So let's say in a database you're saying select count of star from these tables given some conditions and so on, right? So what they're actually doing is basically going to the database, and for every sort of instantiation possible, you're computing how is this true or false, is this true or false in the database, and so on. Right? So very similar. So the problems are very similar here as well. So it's basically like computing the counts of a conjunctive query. So now we'll use these counts within the gradient ascent procedure in the conditional log likelihood learning. So the idea here is that we don't really need the actual gradient. We don't really need the actual value of these expectations, but we need a good enough sort of direction for the gradient, right? That's why we use this approximate counting. So the approximate counting gives us the gradient direction in a sort of approximate manner, even though the magnitude might not be the exact thing that you want. And we also showed that as the counts become more accurate, the parameters learned by this approach approaches the true sort of max likelihood parameters. So what this means is that, let's say that I have I'm doing max likelihood learning on or conditional likelihood learning on this given data set, right? And I learn a specific set of parameters. And now I'm doing this learning using these approximate counting sort of oracles, and I learn a different set of parameters. So as the approximate counting oracle becomes more and more accurate or approaches the true counts, we are going to get results that are equivalent to what you would get in the original when you're doing this original max likelihood learning. So that's the result, which was pretty good. And the other good thing is that existing counters are pretty good at giving excellent estimates of the counts, right? So you have a lot of these UAI inference competitions that go on these days, which is uncertainty in AI, and they have these competitions that which one gives you the best sort of partition functions and so on. And you can go to their website and see that on a lot of these difficult problems, these counters actually give you very close to the optimal or the exact partition functions. So the technology is pretty good now, that people are able to estimate partition functions in a pretty nice way. So this is a way of using that research to compute gradients for us in an efficient manner when you're doing this like discriminative learning here, right? And this was possible because we could encode each formula as this graphical model partition counting problem, right, when you're estimating those counts there. And using this, we scaled up a number of different algorithms for weight learning. So one is contrastive divergence. So the idea in contrastive divergence is you take the same equation, and to compute that second sort of expectation, instead of doing exact inference, you compute it using a few Gibbs samples. So just like in the contrastive divergence approach, where you use Gibbs samples to kind of do neural network learning. So here use Gibbs sample to compute this this expectation, and within these, so when you're computing the expectation, you use a few Gibbs samples, and as I said, you also have to compute each of these Gibbs samples. You need to use the approximate counting oracle, right? So there are two steps here. You approximate E of theta using Gibbs samples, and to compute each of these Gibbs samples, you actually have to use that approximate counting oracle. So similarly, there's another approach, voted perceptron, and this was a way in which you compute that expectation not from Gibbs samples but from the map assignment given the current weights that you have. So let's say that so for the current weight assignment theta, you have a particular map assignment, right? So you compute the counts or that expected value of how many groundings are true for this particular world. You're simply using the map assignment. So again, so to compute the map assignment, we'll use the approximate counting oracle, right? So there are two steps here. So one is computing the expectation, which is a hard problem. So for that, we'll use an approximate inference procedure like Gibbs sampling if you're doing contrastive divergence, or a map inference if you're doing voted perceptron. And to do each of these things like Gibbs sampling or voted or map assignments, we'll use that mapping that we had, which said, how do you compute how many groundings of a particular formula are true efficiently, and so on. So using these two, we can kind of scale up the discriminative weight learning procedure by a lot. So we did some studies here. So these are different sorts of tools for MLNs that are open source, and I'll go over some of them here. So one is called Alchemy, which is the old one. Tuffy is probably the more latest sort of tool for MLN inference and learning. And we can see that the contrastive divergence, voted perceptron, and this other one called pseudo likelihood learning are much more scalable as compared to these other approaches here using these approximate counters. Because the X means that it simply could not run. So again, so you're saying that Tuffy, which is probably the state-of-the-art system, cannot really run on large data sets. So the x-axis is showing what's the size of the data set. So if you use the complete data set, for this, I think the protein interaction problem, what happens as to when you use, let's say, 10% of the data set, 20% of the data set, and so on. So after 20% of the data set, other algorithms don't work, but probably the only way to make it work is using these approximate counting oracles within this weight learning procedure. And the nice thing also is that most of these approximate counters actually have nice ways to control complexity. So for example, in this IJCAI algorithm, there's this thing called I-bound, which can be used to trade off accuracy of what is the partition function value that you get with the complexity of how long it takes to run the algorithm. So you can actually set that to see how much of accuracy you want in these approximate counts, and in turn, how close you want the learned parameters to be the parameters that you learn if you did anything without these approximate counts. So these are for different sorts of problems, and we observed kind of similar results there. So okay, so now let's just take a look at some of the practical software and tools and all these things out there for MLNs, and what are the applications that MLNs are pretty useful in, and some of the applications that have been developed using MLNs. So some basic MLN notation is you have those predicates. So most of these tools also provide some support to do what's called mutual exclusion, which is, let's say I want to do a classification problem, and I want to say that, every page has exactly one topic, right? So if you say I want to say every page has exactly one topic, then you can add that exclamation mark in some of these tools, which says that for every page you should have one topic and you can only have exactly one topic, right? So that's almost like a constraint of mutual exclusion and exhaustive. And again, then you have, you can define different predicates, and then you can relate these predicates using, these constructs as in logic. So for example, if web page P has word W, it implies the topic of web page P is T, right? You can connect these things. But one of the things that is, problematic here is that if you wanted to do this in a real world situation, this formula is not very useful, right? Because what it's saying is that no matter what the word, what the web page, what the topic is, the weight would be the same, right? So you only have one parameter, that connects any possible word with any possible web page with any possible topic, which is just not realistic, right? So there's just one parameter for this model, which is not good. So one way to do this is you can kind of add this plus sign, which simply means that for every different instantiation of different variables, you're learning a different weight associated with it. So this is something to balance out, let's say, bias versus variance kind of thing, which says that, if you want to have many parameters, right, then you'll have lots of these plus signs there, right, which would make learning a little harder as well because you have too many parameters there. But if you have too few parameters, your the model itself might not be expressive enough of the real world, right? So in this case, what we are saying is that for every combination of word and topic, there is a different parameter associated with the MLN, right? There's just not one weight. You actually are going to learn W into T different weights for the MLN, so which is probably a more realistic thing. And then of course you can kind of mix both hard constraints and soft constraints, which simply means that some constraints are things that to be true all the time. So you can add that as a hard constraint, and you can only learn the weights for the soft constraints, right? So because those are things that are not true all the time and you want to weight, but there might be some things that are always true or always false, and you can add them as hard constraints. So these are basically some typical steps that, typical things that you would declare in an MLN in general. So many different types of MLN software. The first one was this Alchemy 1.0, which was developed at Washington. Now this is almost obsolete in some sense because it's not very scalable. So these have some of the most early sort of MLN inference algorithms and learning algorithms. But I think this is still the only one that has structure learning algorithms. So structure learning meaning that I give you data, I don't know what the formula should be, so it has to infer that structure from the data itself. So that's a hard problem. I didn't go over that in detail here, but this is probably the only one that has some structure learning algorithms. And the good thing about Alchemy 1 is that it has plenty of options. So I think it has several different types of learning, inference, algorithms, different parameters, and so on. So this is probably the most comprehensive MLN inference system that has been developed, but it's also problematic because it does not really use lifted inference. So it tries to create this ground Markov network, which simply becomes too large. So for most practical problems that, if you just throw Alchemy at it, it might fail. So that is one of the disadvantages with this particular tool as compared to the more recent tools that are available. But it has most of the popular algorithms, MCSAT, which is a sampling-based inference algorithm, Gibbs sampling, belief propagation, max-walk-sat, and so on. So learning using contrastive divergence, voted perceptron, and so on. And also structure learning algorithms as well. So if you use this, one of the things might be that you'll see that it'll be stuck a lot of time because it's trying to create that ground Markov network. So if I give it, an MLN and, some constants, it is going to create that large ground Markov network before it does any inference or learning. So that means that it's not really applicable for large scale problems. So that's the problem with Alchemy 1.0. So Alchemy 2.0, there is, it's a little bit better than Alchemy 1.0 because it implements some of the exact lifted inference algorithms. So I told you probabilistic theorem proving, or lifted Gibbs sampling, lifted importance sampling, and so on. But again, this only uses exact symmetries. So if you just give it a general MLN, which does not have these exact symmetries or structure in it, it might still be kind of, not so scalable. Simply because it's trying to give you those guarantees, which means that it's not changing the distribution. So this is kind of exact sort of lifting that it is doing. Or when you give it arbitrary evidence, since evidence breaks these symmetries, again, this might not work as well. Right, again, so this is there openly available here as well. But when the right symmetries are present, this is quite scalable. Right, so this is Alchemy 2.0. So Tuffy is basically the latest one, I think, or at least one of the newer ones that's developed at Stanford. And this is based on top of SQL. So what they did is they kind of converted this whole inference and learning into, kind of query-based sort of, into SQL query-based sort of approach, which means that it grounds much more efficiently using database. So it's not lifted inference in general, but if you give it, an MLN as well as this database, or as well as this evidence, it grounds the MLN in a very efficient manner. So it does not create the full Markov network as Alchemy does, but it does that in a much more efficient manner using, technology from databases. Right. So this is that way. It's pretty good at grounding, but still, since it's not lifted inference, there's a limit to how big that MLN can become. So again, so this won't scale up for really large problems in general, but it's pretty robust though, in the sense that it doesn't, hang very often and so on. So this is a pretty nice system to use. But there are only two algorithms that it implements, which is MCSAT and MaxWalkSat, one for marginal inference, one for map inference. So not too many options as compared to like the Alchemy sort of approach. Right, so that's the overview of this particular system in general. So this Alchemy Lite is a new approach wherein instead of using the full first order logic, they'll give you only a specific subset of predicates that you can use. So you can only use things like, is, a, has, a, and things like that, right? So a subset of predicates. And using this, they develop a new language called tractable Markov logic. So using the subset of predicates, you can define inference algorithms that are very efficient. But the problem with this is that you might not be able to represent your problem using just those predicates. So it's not so flexible, right? Because you have so few predicates, so you might not be able to represent your problem with those predicates available. But if you can do it, then inference becomes much more scalable here. Right, so that's the advantage with Alchemy Lite. And if you want to do map inference, particularly, there is this one which uses cutting plane algorithms. So this is pretty good. It's called Markov, the beast. I don't know how the name came up, but again, so it's not lifted inference, but it integrates cutting plane algorithms with MLN map inference. So it's pretty good. But it only gives you map inference and nothing else. A slightly better version of map inference is this one called ROCIKT Rocket, and this integrates ILP solvers into MLN inference, and it's also a parallel implementation. So you have kind of different threads that are working together. So it's a little bit more advanced form of map inference. So this is pretty good for map inference in general. But again, it's not lifted inference, so there's a limit to how much of scalability it offers. So this is something that we've been working on for the past 2 years or so. So this has a lot of the approximate stuff that I was talking about, which does this clustering based approximations, as well as uses these approximate counting oracles to do inference and learning in general. So it does not pre-ground the MLN, so it does not create that large Markov network, and it uses an approximate counting oracle within this Gibbs sampler, and as well as within map inference, and of course this pre-processing to approximately find these symmetries, right? So we don't have, even if you don't have exact symmetries, you can still use approximate symmetries to lift the MLM. So again, so this is still under development, not too many algorithm options, and you can find this code here. So what I also have is, one of my students developed a nice web interface for it, so it might be intuitive to kind of see what I was talking about. So this is like a web interface for that software. Right. So this is the idea here, wherein you can give it the, oops, I think I'm not, hold on. I should go out of presentation mode, I think. So again, so this is just like a user-friendly sort of tool that you can use to do inference. It does not really have learning built in it, the user interface, but the code actually has learning as well, the internal code. So let's see some example here. So let's say I have this MLN, which is, I just had this demo MLN here. Right. So this is an MLN that is, that has all these predicates, and each of them have, 1,000 different. So those 1,000 are saying that X can be instantiated with 1,000 different constants. Right? There are 1,000 constants associated with X for P0, P1, P2, P3, and so on. And these are so few different formulas. And the evidence would look like this, which simply says that some facts are observed. So P0 of, this is just integers, where it can be anything. So P0 of 761 is true, or P0 of 502 is true, and so on. So this is just like the evidence database that is there. And the query can be something like, you want to estimate the marginal probabilities of all groundings of P0, P1, P2, P3, P4, and P5. So you want to compute these marginal probabilities that way. So if you want to take a more user-friendly sort of thing, let me see. So let's see this problem here. So here you're saying that you're encoding the smokers and friends sort of model, which says that if X smokes and not friends of X with Y, implies that Y smokes, right? So this is saying that, two friends are basically smokers. The second one is saying that smoking causes cancer, and then you have, these prior sort of probabilities on smokes, friends, and cancer. And this weight can be, the weight that you learn. So for now, I'm just setting it to something. You can even have negative weights, or you can have small weights and so on. And then your evidence would be some observations. You're saying that 0 is frames with 61, 1 is frames with 7, and so on. And you want to find the query variable as cancer here, which is what is the probability that some object or some person has cancer. So that is the MLN here. So let's say we choose this. So here you can select parametric or not parametric. So with parametric, you can actually choose how much compression you want to do. So let's say 0.1 compression, which means that I'll convert that 1000 objects, I'll multiply it with 0.1, so it basically becomes 100 objects, right? So I have 100 clusters, and I basically take the center of each of them to be the object there, right? So instead of 1000 objects, I have 100 objects now. So you can say that, and I think this one uses k-means, but there are a few different options here. So then it kind of runs this pre-processing steps, and what it is displaying here is kind of some graphs which says for each of these meta sort of objects, how much of evidence does it actually encode. So 0 means that this meta object does not really encode any evidence atoms, and 1 means that whatever is there, this encodes everything is evidence within this meta object, right? So ideally what you want to do is put it at the extremes, because either an object should be evidence or non-evidence, right? When there is this gray area where it's neither evidence or non-evidence, it means that the cluster mixes evidence objects as well as non-evidence objects. So it's not a very pure cluster that way. So this is something like this. But so let's say that we kind of change this to 0.5. Sometimes this has a problem. Let's see. So now what it does is, since there are many clusters, so because 0.5 means that it's a larger CR, so you can kind of get only evidence or only non-evidence sort of clusters, which means that you can approximate the distribution a little bit better. So this way you can kind of trade off this, how well you can approximate this distribution with the number of clusters in general. Or you can even do non-parametric clustering, which kind of figures out the right clusters to use and so on. Okay, so if you wanted to run inference, you can do this. And here you can set this parameter again for this approximate counter. So I said within inference, you can actually do approximate counting. And you can set it in this particular tool. It uses an algorithm called IJCAI, which controls its complexity with this I-bound. So 1 is the smallest value. And so you can then say, okay, and do inference, and it kind of prints out these graphs in a visual sort of manner after every minute as to what the marginal probabilities look like and so on. I think there's a little bit of delay, so after some time we'll start printing it out. Something like this, and it keeps refreshing it, and the marginal probabilities keep changing, and you can observe over time as to how those probabilities look like and so on. So this is more of a visual sort of interface to do that, and once the inference is complete, you can download these results, you can download the graphs and the marginal probabilities of these things. And again, so the learning is not in the visual tool, but it should be there in the actual code in general, where you can actually perform the learning using the weight learning algorithms. So again, so this is the disadvantage of this tool is that it only has one option, which is doing this clustering and running Gibbs sampling. So it does not have still map inference or other types of samplers integrated within it. So it would, it's going to take some time to actually have that. have all the options that Alchemy has so far. But it's probably more scalable, simply because you can control, how many clusters there are, and you can also control how much inference complexity that you want to add by setting that I-bound value when you're doing the counting during inference. And even the learning here uses those approximate antimaticals. Okay, so next part is, yeah.
How are the existential quantifiers treated?
So the existential quantifiers is a pretty much a hard problem in some sense, because when you have existential quantifiers, what you really, one way of treating them is to actually have an OR over all possible grounds. So that is probably the worst way of doing it, right? So there's some, let me think. There was something more recent about handling existential quantifiers. I forget the name of that work, but I do remember vaguely that somebody came up with something to handle these existential quantifiers in a little more efficient manner.
So what about the systems? Do they handle this?
No, these are basically assuming universal quantification.
So
now these systems can handle existential.
Say the first resolution without any existential quantifier.
Yeah, without existential, because existential quantifiers adds that level of complexity, which is.
That I know, but I think this has to be clarified, right? Because you say at some point there's IJCAI and there's a fragment of first resolution.
Yeah.
Which is a tractable fragment.
Yeah, it's a fragment fragment. Yeah.
But the rest is also a fragment. Like all of them are.
Okay. Okay, but yeah, let me take that back. Alchemy does handle existential quantifiers, and so does Stuffy.
Yeah, but that's as a restricted fragment, very restricted way.
Yeah, but what happens is that if you add it, the chances are that your code won't run, because it creates this grounding, which is a very large sort of, or it can be this or this or this or this or this, which simply blows up the size of that model a lot. So which is problematic, I think. So that is something that, yeah. So for handling existential quantifiers is something that I don't think there's a very good solution to that, as far as I know, at least right now.
So you're basically saying the state of the art is basically fading.
Yeah. So that's what is my that as far as I know, that's what it is.
So are you aware of these approaches that do theorem proving and logics and ontologies, because they are proper? I mean, they have these fragments that they can handle extensions.
Okay.
By synchronization or this or that, some other approaches.
Yeah, so as I said, so there was something more recent of handling existential quantifiers, which I haven't looked at, but I still have a vague memory that somebody has, maybe it's even this year's paper or something like that. But again, so I don't have, I don't remember what it was, but it uses some of these colonization techniques to do it.
And how is this semantics even defined if one has extensions? Is it like still over the grounds?
Yes. It's still over the grounds. Yeah, it's still the same semantics defined that way. And one of the, so I think it depends on this sort of application. I know that in a lot of NLP applications, they do require the existential quantifiers, which makes it problematic. So I was working with one of those applications some time back, and yeah, so there we couldn't figure out what to do with the existential one, I think. So yeah, so I'll let the application part of the talk take over right now, and it's basically to do with NLP applications, which is what Dr. Vincent works on. So please.
Okay, so I'm an NLP person. I'm not a machine learning person. And I can tell you that there has been a lot of interest in the NLP community in the past few years to apply Markov logic networks in solving NLP problems. But if you ever applied MLNs to solve an NLP person, you get annoyed at some point, because you can let one of those MLN softwares that Deepak showed you and apply it to your NLP problem, and you realize that it could take days to run the software without getting any results back. And that's why Deepak talked so much about scalability, because some of these MLN software is not really very scalable. And so if you apply it to very large tasks, then it may not be able to return any results to you. Fortunately, since I'm working with Deepak, I don't need to worry about any of the theory. I would just tell him that get results, back to me, figure out, how to improve your software to, so that I can get results back. And so today we're going to look at a couple of NLP applications of Markov logic. Of course, these are not the only applications of NLP to and Markov logic to NLP. These applications selected, for instance, text classification is a classic example of how we can apply Markov logic to NLP problems. Sentiment analysis, of course, is a very popular task in NLP. I want to show you what people have done in terms of applying Markov logic to sentiment analysis. And the last two tasks, coreference resolution and event extraction, are more complex tasks in the sense that, if you're talking about text classification and sentiment analysis, we are just applying or trying to predict values, right? In topic classification or text classification, you're trying to predict the topic of a document, whereas in sentiment analysis, you want to determine whether a text has a positive or negative sentiment. And so in that sense, we are still trying to predict values, whereas for coreference resolution and event extraction, as you will see, we are trying to predict the structure given a document. In that sense, it's more complex. And so let's take a look at the two easier tasks first before we get into the more complex tasks. So let's take a look at text classification. So again, the goal is to label the topic of a web page or any documents that you have in mind from a predefined set of topics. So the topics are given and you just want to pick one of those topic labels and assign it to your document. So here I have two examples. Let's take a look at the second one because it's more simple. The Oscars were a big success, several celebrities gathered, blah, blah, blah. And so in that case, you probably want to assign the topic label entertainment to the second document because it's about entertainment. And similarly, for the first document, you want to assign the label sports to the first document. And the typical assumption that people make in text classification or topic classification is that each page has exactly one label, okay? So how would you solve this problem? Well, the typical approach would be to apply an SVM classifier to predict the topic of each document independently of other documents using features like the words in the document. But of course, the question is, can we actually do better than this by exploiting the relationship between documents? Because there might be some relationships between documents that we can exploit in order to improve classification accuracy. And in particular, rather than classify the documents independently of each other, we want to do joint inference using Markov logic networks. So how can we possibly do that? Well, when you try to design an ML end, probably you remember from what Deepak told you that we need to define the predicates, and we also need to define the formulas that would encode the knowledge that we want to to give the system. And what kind of predicates would be useful for topic classification? Well, we have to define predicate for topic because that's what we want to predict, right? Topic page, topic, exclamation mark. That means that we want to predict that page with this particular topic, okay? And we have an exclamation mark after topic to signify the fact that you can assign exactly one topic for each web page. In other words, the different topic categories are mutually exclusive. And then we have other predicates, has word page indicates whether a given word appears in a particular web page. And the third predicate, link page indicates whether there's a link from one page to another. In other words, whether the page's hyperlink appears in another page. Now that we have these predicates, of course, we try to write down formulas that would allow us to encode knowledge as hard and soft constraints. And one formula that we want to write here is this: has word WP implies topic PT. What that means is that we want to say something like, if word W appears in this page P, it implies that that page P has topic T. Of course, that we have to encode it as a soft formula. We want to learn the weight, to show how, to what extent this formula is true, because it's not always true that whenever you have a given word, then this page will belong to this topic. It's not always true, and that's why we want to model it as a soft formula. But there's a caveat here. This formula is problematic because it learns a single weight for all possible words and topics, right? Because some words are more indicative for certain topics than other, and so you don't want to assign the same weight, for all for all the possible words and topics. And so how do you assign different weights for different combinations of words and topics? Well, we can use this plus sign that you see in the formula at the bottom of the slide. You can see that there's a plus W plus T. What that means is that we want to learn a different weight for each combination of words and topics. And that's why we use the plus sign. Okay, and again, we want to model this as a soft formula so that we will be able to assign different weights for different combinations of words and topics. And one thing that I forgot to mention when I talk about the predicates is that there's this difference between query predicates and evidence predicates. Query predicates are predicates whose values are not known. We want to infer the values of those predicates, and that's why we call topic our query predicate for this problem, because we want to know the topic associated with a page. Whereas has word and link are what we call evidence predicates, because we already know the value of these predicates, because we know whether a word appears in the page, we know whether one page is linked to another. So those are predicates whose values are known, and that's why we call them evidence predicates. And so once we define these query predicates, evidence predicates, and also the formulas, we would be able to apply our MLN. Okay? Now remember, our goal is to model the dependencies between different documents. Would this formula has word implies topic allowed us to model the dependencies between different documents? No. It's just like an SVM if you think about it. This formula says has word WP implies topic PT. It's like an SVM that uses words as features if you think about it, right? Because it's trying to use the words to predict the topic. But if you really try to model the dependencies between different web pages or different documents, we need a different formula like this one. It says topic PT and link PP implies topic P prime T. What that means is that if page P has topic T and P prime are linked together, then page P prime should have topic T. Again, we want to model the dependency between two different pages, P and P prime here. If one page has topic T and they are linked, how likely would the other page has topic T? And again, we want to model this as a soft formula because we want to assign, again, different topics should have different weights for this last formula here. Okay, is it clear how these notation works? But it's a pretty simple application of Markov logic networks. Okay, and of course you can have some improvements like modeling word similarity. For instance, that happy, elated, glad, they mean similar things, and so you can improve possibly classification accuracy by clustering them and treat them as one element rather than separate elements, and that would help us reduce the data sparseness problem. Okay, and you can also similarly cluster related problems to make the problem more scalable. And other task that I want to introduce to you is this fine-grained sentiment analysis task. Some of you already know what sentiment analysis is, and much of the work on sentiment analysis operates at a document level, meaning that given a document, we want to ask ourselves, is the sentiment expressed in this document positive, negative, or neutral? But coarse-grained sentiment analysis may be insufficient. What that means is this. Let's take a look at this example here. Despite the pretty design, I would never recommend it because the sound quality is unacceptable. If I ask you whether this expresses positive or negative sentiments, what would you say? Well, I guess he talked about positive aspect and also talks about negative aspects of this product. And so maybe for this kind of document, it doesn't make sense for us to talk about document level sentiment analysis. What we probably want is fine-grained sentiment analysis. Instead of assigning just one sentiment value to the entire document, we want to assign sentiment value to different portions of this document. In particular, we want to assign sentiment at the discourse segment level. What that means is you can view it as a clause. For each clause, what is the sentiment expressed for that clause? And that's what we call fine-grained sentiment analysis. And so in this example, we would assign sentiment value to each of the three clauses in this example. Despite the pre-design would be one clause, I would never recommend it would be another clause. And so these sentiment values would be assigned for each of these clauses. So again, what would be a simple approach to this problem for assigning sentiment values to these clauses? We can train an SVM classifier to classify each clause or each discourse segment as positive or negative independently of each other. But as usual, maybe we can improve the process by modeling the dependencies between different discourse segments or different clauses. So how, again, can we model the dependencies between different discourse segments? Well, again, we have to define our MLN to do that. As usual, if you want to write down your MLN, you have to first define the query predicates first. Well, in this case, what are the query predicates? Again, they are predicates for things that we want to predict. We want to predict whether a discourse segment X is positive or negative, and that's why we have two predicates. Negative X means that discourse segment X has a negative polarity or negative sentiment, whereas positive X means that discourse segment X has positive sentiment or positive polarity. Okay? And we have some formulas that encode our knowledge about how these predicates should be related to each other. The first one says that if you are not positive, you must be negative. And the second formula says that if you are negative, then you cannot be positive. So this is background knowledge that we need to give the system to ensure that each discourse segment has to be either positive or negative, but not both. Of course, the authors oversimplify this problem in the sense that some discourse segments could be neutral, but of course we can add formulas like that into our MLN. But in this case, they simplify the problem to the case where each segment can only be positive or negative, but not neutral. But again, this is not a limitation of MLN in the sense that you can always add new predicates to model, for instance, that some discourse segments could be neutral in sentiment. Okay? So there are other formulas that we can include in the MLN to capture dependencies between different clauses and different discourse segments. Let's take a look at these different, three different types of formulas for capturing such dependencies. The first one is prior polarity. And so we have these two formulas for capturing what we call prior polarities. Let's take a look at what it is. Typically in NLP, we use a lot of dictionaries to help us build these NLP systems. And in particular, for sentiment analysis, there are three dictionaries that we can possibly use. Don't know whether you have heard of SentiWordNet. For each word, you actually get a polarity value that tells you how positive or how negative that word is. Turney's adjective list actually is a dictionary containing adjectives that shows you how whether an adjective is positive or negative. And Unigram lexicon is another dictionary that tells you whether a word is positive or negative. And you can actually make use of these dictionaries to help you make predictions. And so for the first formula that we have there, positive source L indicates which of these three dictionaries we are using. Positive source X means maybe that source indicates that this discourse segment is positive, then it implies that that discourse segment is positive. And so again, you're trying to correlate, find correlations between whether the dictionary says the segment is positive and whether the discourse segment is actually positive or not. So we are trying to see whether there's any correlation by writing down these two formulas. Again, they are soft formulas. We were trying to learn ways to indicate how close the correlation is between whether the dictionary says whether a clause is positive or negative and whether the clause is actually positive or negative. Okay? And we can also exploit what we call neighborhood polarities. What exactly is this? Well, typically, when you write a review or write a document, if you write one sentence and that has a positive sentiment, very likely the next clause that you write should have the same sentiment. Typically, you won't flip sentiments all the time, and that's where these two formulas come from. If you look at the first formula, it says, X and Y are discourse segments again. So what pre-XY means is X precedes Y. So X is the immediate preceding discourse segment of Y. So if X precedes Y in the document and X is positive, then Y is likely to be positive. Of course, we don't know whether this is true, and so we will encode this as a soft formula. Similarly, the second formula says if X precedes Y in a document, and X has a negative sentiment, then Y probably has a negative sentiment. Again, this may not always be true, and that's why we want to encode them as soft formulas. Okay? And there's another source of information that we can possibly use. We call these discourse relations. If you're not an NLP person, maybe you don't know what it is. Let's take a look at one particular discourse relation called the contrast relation. So when you have two text segments, typically there exists some sort of relation between them. For instance, in our example, we have despite the pretty design, and then I would never recommend it. is there any relationship between these two segments? Yes, there's a contrast relation. If you use the word despite, you want to make a contrast there. And so that's why we said that there's a contrast relation between segment 1 and segment 2. Whereas if you look at segment 2 and segment 3, you know that there is no contrast relation there because you know that the author was not trying to express any contrast relation. The relation between 2 and 3 is an explanation relation because the author was trying to explain why he would not recommend this product. But in this case, we are only interested in contrast relation. We are not interested in explanation or other kinds of discourse relations. So we want to see how we can possibly make use of contrast relations to help us, improve sentiment analysis. Well, we encode our knowledge of contrast relations as formulas like this. If we take a look at the first formula, it says, for all discourse segments X and Y, if X and Y have a contrast relation and X is positive, then probably Y has a negative sentiment because there is a contrast relation, and so they should have differing sentiment. And for instance, if you look at the last one says if there is no contrast relation between X and Y and X is negative, then Y should also be negative. And so that indicates that there's a continuation in polarity if there's no contrast relation between two discourse segments. And so if you add these formulas, then you are essentially trying to encode contrast relation in helping you improve sentiment analysis. And so how effective are these formulas? Well, when the authors evaluated this MLN approach on 3 different topics: cell phones and service, food, kitchen and housewares, and they use voter perceptron for learning the weights of these formulas. Here are the results. Again, you have precision recall and F-score for both positive and negative. The last row of the table shows the accuracy. The first row, last column shows the accuracy. The first row of the table shows the majority baseline. In this case, you just predict everything as negative. And so you can see that you can achieve an accuracy of 51% if you just predict everything as negative. The second row shows what happens if you use an SVM classifier, no MLN. You train an SVM on the words as features, and you can see that it actually performs better than the baseline by quite a bit. The last 3 rows shows what happens if you use polarity only, you model neighborhood only, and use contrast relation only. And you can see that the best system that that we have here is the one that models neighborhood but not contrast relation. Well, why would not modeling contrast actually gives you better results in this case? Because it's actually not always accurate to detect these contrast relations. I showed you that simple example, this word despite, and if you have that word, then it's easy to detect the contrast relation. But there are many contrast relations that are not explicitly realized by words like despite, and so there are errors in detecting these contrast relations. And so in the end, when you try to incorporate contrast relations, you actually get worse results than if you don't try to model contrast relations. Okay. Now let's move on to the third application, which we call entity coreference resolution. Again, this application is more complicated in the sense that you're trying to predict a structure now rather than just a value. But before that, let me see what question.
On the last column, were you saying that you were just using polarity and contrast independently? And the question is, why didn't you combine them?
If you think about it, neighborhood contrast actually make use of neighborhood, right? If you take a look at the contrast relations. If you look at the last formula for making use of contrast, the last one says that if you don't have any contrast between 2 discourse segments and X is negative, then Y has to be negative. It's modeling neighborhood already, right? And so one is actually incorporating the other, even though I said that you're not doing them together, you're implicitly but not explicitly making use of the other. Okay. So let's see why this task entity coreference resolution is harder to model as an MLN problem than the first 2 tasks. But let me remind you what entity coreference resolution is. The goal is to identify all the noun phrases that refer to the same entity in the real world. Let's take a look at this example. Queen Elizabeth set about transforming her husband, King George VI, into a viable monarch. Locke, a renowned speech therapist, was summoned to help the king overcome his speech impediment. And so in this case, a coreference system should identify Queen Elizabeth and her as coreferent because they refer to the same real-world entity, Queen Elizabeth. Similarly, husband, King George VI, the king and his are coreferent because, again, these phrases all refer to the real-world entity, King George VI. And finally, log and a renowned speech therapist should be coreferent because, again, these two phrases refer to the same real-world entity, log. And these underlying phrases, a viable monarch and speech impediment, are singletons because they are not coreferent with any other phrases in this paragraph. And so you can see that entity coreference is a clustering task because we are trying to cluster these noun phrases so that each cluster contains all and only those noun phrases that refer to the same real-world entity. Correct? Well, here are the main steps in a coreference resolution system. The first step would be to detect all these mentions or noun phrases, right? Because if you don't even detect noun phrases, what are you trying to cluster, right? And after mention detection, typically what people do is they try to train a binary classifier to classify whether a pair of noun phrases is coreferent or not. So for instance, the classifier would tell you whether Queen Elizabeth and her are coreferent, whether Queen Elizabeth and King George VI are coreferent. So you apply this binary classifier to make a binary decision for each pair of noun phrases or mentions in your document. And after doing pairwise classification, we have to cluster, right? Because if you make binary classifications and try to put together into clustering, it doesn't work because they may be contradictory decisions because transitivity may be violated if you try to create a clustering out of these pairwise classifications. And that's why we need a separate clustering step for putting these pairwise classifications together into a partition or a clustering. Okay? And these two last two steps, pairwise classification and mention clustering, typically are performed in a pipeline fashion. So you have to do pairwise classification first before you do mention clustering. What's the problem here? Error propagation. If you make a lot of errors in pairwise classification, and when you try to create a clustering out of these pairwise classifications that are erroneous, then you are going to encounter a lot of errors in your output. And so what people try to do is, can you actually do these two tasks together using joint inference? Instead of doing it in a pipeline fashion, do them together so that there won't be this error propagation problem. How can you do joint inference over these two tasks? Again, you can try to model this problem as an MLN. And again, when you try to model the problem as an MLN, the first step is to define your predicates. What's the query predicate? In other words, what's the predicate we want to answer in this case? We want to know whether two mentions X and Y are coreferent or not coreferent. And so we have this coreference predicate. Now, once you define your query predicate, you have to define your evidence predicates, right? Evidence predicates, again, are those predicates whose values are known. So for instance, you can define a bunch of predicates that capture properties of a mention. For instance, the first predicate there is mention type I. So we want to know whether mention I has this mention type, whether it's a pronoun, proper noun, or a common noun. Second predicate, entity type of I, we want to know whether mention I is a person, organization, location, etc. Third one and fourth one, gender type, number type, we want to capture the gender number of this mention. Whether this mention has head, whether this mention has this particular head. First mention I, whether this mention I is the first mention in the sentence. And we also have a number of other predicates to capture the fact that this mention may be reflexive, possessive, and so these are different linguistic properties that we may want to capture about this mention. And there are predicates that capture the relationship between these two mentions, because ultimately we want to know whether two mentions are coreferent, right? And so we want to have predicates that capture the relationship between two different mentions, J and I. For instance, the first one captures whether mention J and mention I has this distance. We want to capture the distance between the two mentions. Mention in terms, the distance between the two mentions in terms of the number of intervening mentions and the distance between the two mentions in the number of sentences. And then we have a bunch of other predicates that try to capture other properties of these two mentions. Now we need formulas, right? We define the predicates. Now we need the formulas. What are the formulas that we have here? Let's take a look at the first one here. Well, the first one says if mention J has type T1, mention I, and their strings match exactly, it implies that I and J are coreferent. Is it always true? No, and that's why we would define this as a soft formula and have MLN learn the weight for this formula for us to tell us how likely that this formula is true. What about the other ones? The other ones are very similar. Once you know the types of mention J and I, you want to see, if they have a pronoun match or proper name string match. You want to see whether they are coreferent or not. And so if you think about it, these, if you use an SVM to solve this problem, these would be features, right? If the two mentions have exactly the same string, that will be one feature for your SVM. If in the second formula, if there are two pronouns and their pronoun string match, then you want to use that as another feature. And so, if you use an SVM approach without using any MLNs, each formula would be encoded as a separate feature. And we can have some other features. For instance, under semantic features, the first one says if mention J has type T1, mention I has type T2, and they're alias of each other. What that means is that, for instance, IBM and International Business Corporation would be alias of each other. If that's true, then I and J will be coreferent. Again, that would be a soft formula, and the MLN will have to learn how likely that this is going to be true. But again, you can imagine that this would be another feature in your SVM if you use an SVM approach. But in an MLN, we will encode these features as separate formulas whose weights are to be learned during the weight learning process. Okay? And there are, of course, these other local formulas that we won't bother looking at. There is another type of formulas that the authors call global formulas that try to capture global properties. If you think about these what we call local formulas that we just talked about, they are restricted to looking at only two mentions at a time. For instance, in this case, I have this distance feature that says if mention J has type T1 and mention I has type T2, and the sentence distance is this, then they are probably coreferent. They are just looking at two mentions at a time, but coreference is a clustering task, and so you want to look beyond two mentions, and that's the purpose of these global formulas, because you are trying to look beyond two mentions. So what kind of global formulas can we enforce for the coreference problem? Let's take a look at the first formula. We have three mentions, IJK. If J and K are coreferent, K and I are coreferent, then J and I are coreferent. What constraint are we trying to encode here? Transitivity, right? We're talking about clustering problem, and so we need to enforce these transitivity constraints. And we have two other similar constraints because we have three, mentions here, and so we need two more, transitivity constraints to encode, transitivity for this problem. And we call these global constraints because if you enforce, these three formulas, then in the end, what MLN would give you as the output would be clustering that satisfies the transitivity constraints. Okay? If you don't have these formulas, then all MLN will return to you will be these pairwise classifications that may not satisfy the transitivity constraint. Okay? And so with these formulas, you would end up with a partition or a clustering in the end as the output of your MLN. Okay? So here are some results of using MLN. Again, we evaluated this on this what we call Cornell 11 shared tasks. So in NLP, we always organize these shared tasks where people participate in the shared tasks to compare the results of different systems to understand what the state of the art is. And so in this shared task, we are trying to measure the performance of coreference resolution systems. This table looks complex because there are many different evaluation metrics that people use for coreference resolution, but what we really care about for the purpose of this talk is the last column. And so if you just look at the number in the last column, we'll see the performance of different systems. The first one is using MLN with only local formulas. We don't apply transitivity at all, and so you can see that we achieve an F score of 57 or 56.8. The second line shows what happens if you use the local formulas plus transitivity. But transitivity is not encoded as formulas. We just apply MLN to learn the weights for the local formulas. And then after we get the output from the MLN, we apply as a post-processing step some formulas for enforcing transitivity after we finish learning the MLN. And in that case, we obtain some improvement. But if you actually use those formulas as part of the MLN, in other words, you try to learn, the weights in the presence of those transitivity formulas, then you get even more improvement. So I don't know whether people understand the difference between the second row and the third row. In the second row, we apply transitivity outside of the MLN as a post-processing step. We try to post-process the MLN output without actually using transitivity inside the MLN. So we try to fix the transitivity problem outside of the MLN. Whereas, in the third step, we actually use the global formulas that we talk about as part of the MLN. And so what these two rows of results show is that if you actually enforce transitivity within the MLN rather than as just the output, then you actually get better improvement. Okay. So let me mention to move on to the last application, which is event extraction. This is even more complicated than coreference resolution in the sense that in coreference resolution, if you look at these formulas, these local formulas, again, if you remember what these local formulas represent, each of them can be viewed as a feature that would be used by an SVM. And so you can see that there are quite a number of formulas because for coreference, you do need a number of features for doing prediction. Whereas for event extraction, there would be millions of features. And so if you really try to use that same approach that we have here for encoding features for event extraction, you would end up with millions of formulas. And of course, that would not be feasible because MLNs in general are not as scalable as we want, and so we will not just be able to apply this brute force approach of encoding features as formulas in the MLNs if you try to apply it to event extraction. So there must be something that we need to do in order to be able to apply MLNs to event extraction. So let's see what we need to do. Well, let me define the task for you first. The goal of event extraction is to extract and label all instances in a text document that correspond to predefined event types. So as usual, just like topic classification where you're given a number of topics, in event extractions, we're also given a number of event types, and you want to extract instances that belong to a predefined set of event types from a document. And that's the goal of event extraction. And the approach that we talk about is an approach that Deepak and I and other students developed in 2014. And the particular event extraction task that we focus on is this GENIA event extraction task that focuses on extracting instances of biomolecular event types. So let's take a look at this example to help us understand what biomedical event extraction is. Blah, blah, blah demonstrated that HOIL1L interaction protein, HOIP, is recruited to CD40 in a TARF2 dependent manner. So from this text fragment, we are supposed to extract two events, E11 and E12. Okay? So each of these two events is represented by its event type, a trigger, which is a word that identifies the event known as a trigger. And finally, there are arguments associated with each event, and the arguments are the participants of the event. And so let's take a look at each of these two events to better understand what an event is. The first event is a binding event, so it's the event type, and the trigger is recruited. So this event is triggered by this word recruited. And the participants or the arguments of these events are these two things, interaction protein and CD40. And each argument actually has a role played in this event, and they both play the role theme in this event. Whereas in the second event, E12, is a regulation event, is triggered by this word dependent, and it has two arguments. It has a cause argument, which is TARF2, and it has a theme argument, which is event E11. So what that means is that events can be recursive because the argument of one event can refer to another event. And so regulation events can be nested. And so this is what makes this problem complex, because you're not just extracting simple arguments, because another event can become an argument of some other event. Okay? So the task is to extract instances of 3 different event types. Regulation events, we saw that. One protein or event as its theme argument, and optionally one protein or event as its cause argument. That's how people define the regulation event. And it's the most difficult to extract event type because it has a recursive structure. You can take another event as your argument. And also this cause argument that regulation events have can be optional. And so sometimes you don't need this cause argument. That also makes it difficult to extract regulation events. A binding event is simpler to extract. It only contains one theme arguments. You can have more than one theme argument. In this case, it has 2 theme arguments in 11. So you have HOIL1L interaction protein as one theme argument, CD40 as another theme argument. So in this case, you can have 1 or more proteins as its theme argument. But there is no recursive structure. In other words, these theme arguments cannot be another event. So there's no recursion in these binding events. And finally, we have a very simple kind of event that people simply call simple event. It can only contain 1 argument, which is a theme argument. Okay? And so event extraction has 2 key subtasks. The first step typically would be to perform what we call trigger extraction, because you have to identify the word that triggered the event. And at the same time, we want to identify the event type. Okay? So that's what people call trigger extraction. And the second subtask of event extraction is argument extraction. Once you extract the trigger and its event type, you want to extract the arguments associated with an event, as well as assigning a role to each of the arguments. Is it a theme argument or is it a cause argument? Okay. How would you do trigger extraction or argument extraction? The simplest approach would be to apply a pipeline approach, where we first train an SVM, or using your favorite learning algorithm, to identify the triggers and assign an event type to the trigger. And after that, again, when you use SVM, sometimes you may have to use millions of features that encode the n-grams and also the dependencies among the words. And so it's a very large feature space. And then the next step, of course, once you identify the triggers, you want to identify the arguments or the participants of that trigger, and assign a role to each of those arguments, whether it's a cause argument or whether it's a theme argument. And after you do argument extraction, again, can take a lot of features. In this case, we actually use 3 million features for training this argument extraction classifier. But after you finish argument extraction, you can combine these triggers and arguments that we extracted into actual events. The first 2 steps, trigger extraction and argument extraction, are the difficult steps, whereas the third step, where you try to put together these triggers and arguments into a single event, that is a fairly straightforward step. And so let's see how we can improve the first 2 steps, argument extraction and trigger extraction. Well, if you want to improve this SVM-based approach, you have to understand what is not good about this SVM-based approach. It cannot help you exploit relational background knowledge. But what is the relational background knowledge that we have for this problem? For instance, a trigger has a theme argument. Well, if we try to train an SVM, there's no guarantee that the SVM will always assign a theme argument to any of the arguments that it's trying to classify. Another constraint that we want to enforce in this problem is a simple or binding event does not have any cause argument. If you remember, the only one type, the regulation event, has cause arguments, whereas simple and binding events do not have any cause arguments. How can we enforce this constraint? Finally, an event with an argument as a trigger is a regulation event. Again, in a regulation event, we have these recursive structures. And so yes, and that's why an argument containing a trigger has to be a regulation event. And so again, the SVM classifier won't allow you to enforce this kind of constraints. How can we possibly enforce these constraints? Well, as you can imagine, we can try to enforce these constraints in an MLN. But typically, if you don't use an MLN, you can enforce these constraints using some post-processing heuristics if you want. But let's see how we can possibly enforce these constraints using an MLN. But another problem with this SVM approach is error propagation. you train the trigger classifier first, and then you train the argument extraction classifier after the trigger classifier. And so if you have errors in trigger extraction, those errors would propagate to argument extraction. And so there is this error propagation problem in the SVM approach. And so the MLN may help us address this problem as well. And so again, the two key weaknesses of the SVM or the pipeline approach is that, first of all, cannot really enforce the kind of constraints of background knowledge that we talked about. And also, because you are doing things in the pipeline where you first do trigger extraction before argument extraction, you have this error propagation problem that propagate from trigger extraction to argument extraction. And so even though these pipeline approaches have these two key weaknesses, they actually achieve state-of-the-art results on our event extraction tasks. That's a bit surprising. But of course, again, as usual, we want to see whether we can improve on the state-of-the-art using Markov logic networks. Well, again, how can you use Markov logic networks? We have our trigger classifier provided by training an SVM. We have an argument classifier also trained using an SVM. But at the same time, we want to include background knowledge in the learning process. And so what we want to do is, again, these are from the SVM. We have background knowledge. We want to feed all these three things into our joint inference engine so that this joint inference engine would use these two sources of knowledge, the background knowledge and the knowledge provided by the SVM, to jointly extract triggers and arguments. Jointly means that we don't do one thing before the other. We do both trigger extraction and argument extraction at the same time, okay? But the question, and so hopefully if you look at this architecture, you realize that you can address the weaknesses of the pipeline approach. First of all, it employs background knowledge, whereas in the SVM, it cannot really employ background knowledge. And second, because we are doing trigger extraction and argument extraction at the same time, it addresses the error propagation problem, okay? And so the question is, how can we encode background knowledge? And which framework can be used for joint inference? Of course, we know that we're going to use MLNs for joint inference, but the question is, what kind of background, or how can we encode our background knowledge? Well, we encode our background knowledge, using first order logic formulas because we are using MLNs, and we have to define our query and evidence predicates for this task as usual. For our MLN, which we call BioMLN, we define three kinds of predicates. First kind of predicates as usual is the query predicates. Again, those are the predicates whose values we want to predict. What are the values we want to predict in this case? We want to predict whether a token is a trigger or not. And if it's a trigger, what is the type of the event that it's signifying? So you have to see that trigger type SID, TIT, TD type. What does it say? It says that if this token appears in sentence ID, SID, and token ID, TID, it has this type, TT type. And so again, you want to know whether a token that appears in a particular position in the document has a particular event type. And similarly for argument role, we want to see whether a token appearing in a document has a particular role with respect to a particular trigger. Those are what those two predicates are for. We want to predict again the trigger's type and also the argument's role with respect to a trigger. So this is what I just mentioned. Again, you have this exclamation mark there to signify the fact that you cannot assign more than one event type to each trigger. Each trigger can only have one event type. There are these hidden predicates. You don't really need them, but defining them makes the MLN easier to read. In this case, we have two hidden predicates. Simple indicates whether a given token in a document is a simple event or a binding event. Whereas regulation indicates whether the word at a particular position in the document signifies a regulation event or not. And finally, we have these evidence predicates. As usual, these are predicates whose values are already known. So for instance, we have this word predicate that tells us whether this is the word that appears in a particular position in the document. And dependency type tells us whether two words have a particular dependency type in a given document. And so again, these are things that we can easily obtain from a document, and their values are known. And so we'll use them to define our formulas. So in our BioMLN, we actually use 9 formulas to indicate or to encode our background knowledge. Let's take a look at the first 2. For instance, the first one says that each token has a trigger type. Is it always true? Yes. If a token is not a trigger, we'll just assign an extra type none to it to signify that token is not a trigger. The second formula says that some token plays this argument row of another trigger. Okay. For each token, we want to know what is its argument row with respect to another trigger. But of course, if you are not an argument of some trigger, then you will have a non-argument row. Okay. And then we try to define the hidden predicates, simple predicate and regulation predicate. Again, what is a simple event? A simple event is true if you have one of these types. And then formula 8 defines what a regulation event is. If you are a regulation event, then you must belong to one of these types. So it's just a definition of simple and regulation events. And then we have these formulas that try to capture the relationship between triggers and arguments. So for instance, the third formula says that if your trigger type is not none, then there exists an argument row that has the row theme. What that means is that if your trigger type is not none, you must be an event. And if you're an event, you must have a theme argument. That is what that formula is trying to encode. If you look at the fifth one, it says that if your trigger type is, if you are a trigger type and your trigger type is none, then your argument row is also none. That means that if you're not a trigger, you cannot possibly have any arguments. Okay? And then we also have some more formulas that encode the relationship between triggers and arguments. The fourth one says that if you are a simple event, then you cannot possibly have a cause argument. The sixth formula says that if your argument row is not none and your trigger type is not none, then you must be a regulation event, right? Because if you remember what a regulation event is, if your trigger type is not none, that means that you are a trigger. And if the first one says not argument row means you're not, if your argument row is not an argument, means that you are an argument and you are also a trigger. If you're both an argument as a trigger, that means that you must be in a regulation event, because only regulation events can have events as arguments. That is essentially what that formula is trying to encode. Okay? And so we have a bunch of formulas that are hard constraints. Weight associated with each of these formulas is infinity. Whereas we have one soft constraint here that tries to capture the relationship between words, trigger types, and dependency types and argument rows. Okay, and so only the weights associated with the last formula need to be learned. Okay, and we also, of course, have to do weight learning because we have one formula that is a soft rule. And so Deepak talked about using voltage perceptron for weight learning, and so I'm not going to repeat how we do weight learning here. And of course, if you remember, we said that for event extraction, we need to, just like using an SVM approach, we need to encode the features used by SVM as separate formulas in the SVM. But since we have 3 million features in our SVM, we cannot possibly encode each of those 3 million features as separate formulas in our ML, that's just not feasible. And so what we did instead is we actually take the predictions of the SVMs as as information that we can exploit in our MLN. So for instance, if you think about what those 2 SVM classifiers do, we have an SVM trigger classifier, we have an SVM argument classifier, and so you can think of the output of those two classifiers as helping or giving us information on how likely a particular token belongs to this trigger type and how likely a particular token belongs to this argument row of some other event. In other words, those two classifiers actually are kind of providing information on how likely these two query predicates are supposed to be true. Remember that we are trying to predict the values of these two predicates, and the SVM classifier is actually providing information on how likely these two predicates are going to be true. And so what we can do is we can treat the knowledge provided by the SVM classifiers as prior knowledge for our MLN, and we can encode the predictions of the SVM as weights for these these clauses, and so we can exploit them as prior knowledge to help us predict whether a token belongs to this trigger type or whether this token belongs to an argument row of a certain trigger. Okay. And so what's next? We can do inference, right? We now have the output of the SVM as prior knowledge. We have encoded our formulas as hard formulas and soft formulas, and so we can try to use SVM to do map inference to help us predict the trigger type and the argument row. But unfortunately, this is still going to be computationally infeasible, because if you try to do map inference over a document, you have to do grounding over the entire document. And so if you have a very long document, which is typically the case in these biomedical events, because typically what we are given as input would be these biomedical scientific papers, and so they have a large number of tokens. And so if you want to do grounding for each token that appears in the document, you would end up with a very large MLN, and that's just computationally infeasible for us to do MAP inference. And so what we need to do is to instead do map inference over the entire document. We want to do map inference per sentence. In other words, we try to create an MLN per sentence rather than an MLN per document. So for each sentence, we would create an MLN. Why can we possibly do that? Because if you remember the way we modeled this problem, we never defined predicates that would allow us to capture relationship between different sentences in this case. We tried to model the relationship between triggers and arguments within the same sentence, but we never tried to model the relationship between triggers and arguments across sentences. And that's why we can do inference for each sentence independently of other sentences. Okay? And so once we do inference for each sentence, we can just take the union of the output, and that would be our map inference for the entire document. And so let's take a look at some evaluation results where we're trying to compare our MLN approach with the SVM approach. There are two standard data sets that people use. One is the BioNLP 13 data set, and the other one is the BioNLP 11 data set. If you look at some statistics that we have here, you'll see the main difference between the two data sets. The 13 data set has this number of papers, so we have three numbers, 10, 10, 14. That tells us the number of papers in the training set, the development set, and the test set. The 13 data does not have any abstracts. Abstracts are easy because they are short, and so the 13 data set is more challenging than the 11 data set, because you can see that the 11 data set has mostly abstract and very small number of papers. The papers are the documents that are long and hard to do event extraction, and so the 13 is supposed to be a lot more challenging data set than the 11 data set. Okay? And so here are the results of the MLN approach, which is shown in the first line of the table in comparison to the top systems on this BioNLP shared task on the 13 data set. And so you can see that our system outperforms the top system in the shared task by quite a margin. And then if you try to compare the Markov logic network approach with the SVM approach, you can see that we beat the SVM by quite a bit by encoding background knowledge and doing joint inference rather than in the pipeline approach. And if we look at the performance of SVM and MLN on the regulation events, remember the regulation events are the difficult events to extract because they have a recursive structure. You can see that MLN actually performs quite a bit better on the regulation events in comparison to the SVM, and that again shows that employing background knowledge actually helps us extract these complex events correctly. if you look at the results on the 11 data set, you can see that our system still outperforms the best system in the shared task. The best system, MIWA12, in the shared task actually makes use of coreference information, whereas our MLN did not make use of coreference information. And so we hope that by incorporating coreference information into our MLN approach, we can get even better performance than what we have now on this 11 data set. Okay, as I mentioned before, the applications I talk about are not the only applications of Markov logic to NLP problems. People have actually applied Markov logic to a number of NLP tasks, and so I included some of these in case you are interested in seeing some other NLP Markov logic network applications to NLP problems. Okay, any questions at this point? If not, then I guess I'll have Deepak come over to summarize the tutorial.
So these are some of the recent applications that have been using MLN. So mostly these have been used in NLP, but there are a few of them that have recently come out that's used in like social network graph mining. That was an interesting application, I thought. And health informatics, kind of predicting things from Twitter and things like that, which use the MLN. So there's been a little bit of interest in different sorts of applications that use this as well. But again, the challenge is, of course, to get it working scalably. So if you looked at all the applications that Dr. Nick talked about, there was a lot of, you can say a lot of things that we had to play around with to actually get it to work. So it wasn't a black box setup where we just took the MLN and fed it to an existing system and we could get results out. So that doesn't happen. So what ideally would be the situation is that you can use some of these approximations and things like that I was talking about to actually make it such that we don't need these domain specific heuristics or information. So an application designer should be able to kind of go ahead and develop applications and give it to this system and it should simply work that way. So in some sense that the bottleneck is basically the lack of these scalable learning and inference systems in general. So the software is not good enough to handle these kinds of problems, I think. And so I think the most promising approach that is out there is, you might have to trade off some of these strong guarantees and theoretical guarantees with some more heuristic measures that way. So clustering and things like that seem to be the direction that people are interested in to make this scalable to large scale problems. And approximate lifting and learning seem to be the most promising directions to achieve desired scalability. And hopefully with this, we wouldn't have to kind of invest a lot in domain specific heuristics and have a more generic system to kind of use MLNs with different applications in general. One thing also is that, joint inference seems to be the most viable topic for, or the application that most people care about with respect to NLP at least. And earlier, I think joint inference was mostly done using ILPs and things like that, which is more of a propositional approach. So we can think of MLNs as being like this lifted way of doing joint inference in some of these tasks in general. So with this, I'll ask if anybody has any questions. I'll be happy to answer it. Okay, so if you have any questions, you can also email me or anybody and we'll be happy to know. And if you have any trouble using the software, just send it to me. And I'll be happy to take a look at it and see if I can help with that. Okay. Thank you very much.